So now we're going to have Joshua Neal. Dr. Joshua Neal is an award-winning data scientist and cybersecurity expert, PhD statistician. Dr. Neal has led teams in development of cutting-edge anomaly detection solutions for enterprise security for over 2 decades. He now leads Microsoft Defender Advanced Threat Protection EDR data science team, introducing new data-driven solutions into Microsoft products that protects millions of customers worldwide.
Thank you. I can't see anything. Thanks a lot, and wow, that was a great talk from Gabe. Stole all my thunder. So I think I'm just going to stand up here and tell jokes. What happened to the frog who parked illegally? Anna knows, and she's somewhere in the back. He got towed. He got towed. Okay, all right. Trying to warm the audience up a little bit. Yeah, I'm Josh. I lead the data science team for Microsoft Defender Advanced Threat Protection, the EDR portion of that. What's EDR? So I'm going to talk a little bit about our technology because that's going to give you some context for the kind of graphs that we look at. So this isn't a sales pitch. I'm just trying to describe what we do. It's an EDR technology. That means there's an agent running on the endpoint. This could be an endpoint in the cloud, a virtual machine, but most of our machines are physical. If you've got Windows 10, our agent is in there. It's a matter of whether it's turned on or not. We also have down-level versions as well. And it's an enterprise product, and what it does is it measures telemetry from the operating system and sends it to Azure, and in Azure, we try to find attackers. Since I run the data science team, we try to find attackers with math and statistics and advancing the slide deck as well. I've got 4 buttons. If I push all 4 and none of them work, then I have exhausted my, oh, what is that button? That turns it on. That turns it on. A 5th button, and hello. What's going on? Maybe it's not talking. Do I have the, I don't have the dongle. That's what's happening. So I'm going to have to flip it from here. Yeah, here's a bit of an outline. I typically skip that. So artificial intelligence, yeah, we do statistics. This isn't meant to insult anybody, by the way. It's just to give you a framing for what we do. Thank you. I feel like a complete idiot. Now I'm standing in front of a couple hundred people. Thanks. OK, magic and magic. OK. Yeah, we do. So we do mostly statistical methods to find attackers in computer networks, and that sort of looks like a graph. Now, Gabe gave a lot of fodder for you guys to think about, and a lot of things that I agree with very much after 20 years of playing with this kind of data. You're going to see a lot of visualizations from me. Actually, we just do computing. And the graph is the topology upon which we work and the ways in which we combine data together. But we don't actually do a lot of visualization. We just use computers to analyze data. And the data has a topology, which is a graph. It's helpful for me to visualize it for you guys so I can explain some concepts. But I'm not actually presenting these to customers for the most part. You might see a couple towards the end. Why statistics as opposed to machine learning? So there's a big topic. We could spend a few days on that, probably. Actually, the math is the same in many cases between statistical methods and machine learning. It's the same math. We typically like to build, as Gabe said earlier, sort of simple statistical models which are easy to update, which have parameters which help us understand the data, and therefore help our customers understand what we're finding in the data. So statistical methods with interpretable parameters for the most part, and and on graphical data. OK, that's a pretty good background. There's a graph. Yeah, that's pretty useless from a computing perspective, but it does help me sort of explain what I'm talking about. So this is an enterprise network. The nodes are computers, little tiny dots. The edges are network communications in the form of net flow, measured from the routers and the switches. And I'm really just trying to tell you, yeah, our job is to find a sort of tiny little bit, which is represented by the blue here, of a lateral movement of an attacker through the network, eventually stealing data. And we use a lot of things to do that. Threat intelligence up at the top. Do I have it? Yeah. So this is just sort of telling us about the internet, you know, and reputations on the internet and things that we should be sensitive to as they start to penetrate the network. This here is phishing, and somebody clicked. By the way, don't click on anything ever. Don't ever click on anything. Lateral movement. There's several elements of this which I'm going to go into later. It's not just, OK, I have a credential, I'm moving around the network, yay. It's more like there's reconnaissance, there's installation of persistence, there's command and control. But eventually, you know, they get to the right places in the network, they've got the right data, and they steal it out of the network. And so I'm actually going to spend a little more time on those elements here. I'm sort of walking you through, I'm setting things up, because at some point I'm going to tell you methods for how we can find this kind of thing. And probably this is pretty well understood by many in the audience in terms of attack behaviors. It's also a gross simplification. And I'm skipping lots of stuff. And this isn't the only thing they do. So just bear with me in terms of explaining some of these methods, because it's a general sort of framework for attacks, but actually specifically wrong in almost every setting, if that makes sense. Just helps me explain. So initial penetration. And I'm going to talk about a couple of concepts here. One is nodes and edges. OK, that's a graph. But another is that attackers introduce deviation from what we expect. And that's where we get into anomaly detection. It turns out the attackers don't tell us a lot. If I go back, they don't actually tell us they're doing this. We don't have labeled data. And so not only do we not have labeled data, but if you can imagine that, well, you know, OK, that didn't work because we predicted it somehow with supervised machine learning, then they may just go over here instead. And so even if we did have labeled data, I would postulate that we don't have representative labeled data of the number of different things that the attacker could do because of the big complexity and combinatorics of a graph. They don't have to move from A to B. They could move from A to C and from C to D. And that kind of thing blows up exponentially in terms of their options. So for those two reasons, they don't tell us what they do. We don't have good labeled data. And the data of today is not necessarily representative of the attack behaviors tomorrow. We typically do unsupervised methods. So that's going to sort of set up some of the discussion about the attack behavior and what we're going to do about it. So the nodes are computers in this case, or they could be users, or they could be any kind of entity that we can observe. In this case, cartoon, it's a phishing email sender somewhere out on the internet. And the edges are some kind of observable communication. Actually, they don't have to be observable. They could be inferred, and we could figure that out from similarity or other things. But in this case, it's an observed email being sent from a phishing sender on the internet to a set of users inside of the enterprise. And again, cartoon. There's a perimeter here, just so you know what's in the internet and what's in the enterprise. Okay, and so yay, a phishing email. Somebody's going to happily click. Many people will click on these things, and then the next thing that may happen is that the browser is directed to a malicious website, and then malware is downloaded and installed. By the way, I didn't mention, but red means there's been a change from what we expect. So actually, let me back up a little, because I have more time. So I'm going to fill my time up here. So imagine examples of deviation from what we expect. Okay, okay, you got the natural language in the email, right? And so you can ask questions like, is there bad grammar, or is there spelling mistakes? What's the tone of the language? Is it trying to get you to do something like click on an email? Is there a link in it? Those things have some deviation or some scoring that we can do, okay, to estimate the probability that this is not a phishing email. And I said not a phishing email, not is a phishing email, because we mostly model what's normal and quantify deviation from normal, okay? So what's the probability this isn't an email? Another one that some people have thought of, I actually haven't seen it published, but maybe it is how uncommon is the set of recipients for this email with respect to how our organization normally receives emails? And we could probably quantify that. For example, our CEO, Satya Nadella, and I don't receive a lot of the same emails. I wouldn't mind receiving more in common with him, but normally, if I get an email and he does, yeah, that's a little weird. It's not a smoking gun. None of this is a smoking gun, and I'm a statistician, so I don't do zeros and ones. I don't know, maybe kind of, 0.2, 0.01, that kind of stuff. That's what floating numbers between 0 and 1 actually is sort of what I think about. So with all of these things, sort of evidence of it's not a phishing email put together, I'm going to be able to score the red that I'm seeing here in terms of how much deviation the attacker has introduced from what I expect. Again, attack. So the user clicks. What's the reputation of that website? Is it new on the internet? Is it linked by other websites? What's its reputation? There's lots of ways to do this and lots of literature and techniques to do this. But what I want you to get the idea of is there's a score associated. We can put a score associated with the edge. The fact that this machine went to that website. What's the score for that? Reconnaissance. So yeah, turns out that was malicious. Let's say there was a 0-day, an exploit. They got in, they're on the operating system. They got a credential. They're logged into this computer from outside through the firewall. That's a breach. That's what EDR works on. That's what we try to find is after they've done that. The attacker may explore the network. So one of the advantages we have as defenders is we know what's normal, right? Or we can know if we have good visibility and actually bother to try to understand our networks. And yet the attacker, to some extent, and some of you may be more sophisticated at this than others, but to some extent they won't know what's in the enterprise until they get in, and they'll have to explore. So you'll see port scanning. That's one way to do it. So they're on the box. They'll horizontal port scanning. That's where they've got one thing they're looking for, like SQL. They're looking for a database, right? An SQL. And so they'll emit ping requests or some other kind of login requests or something else to try to find SQL servers among a whole bunch of machines out there. Or actually in credential escalation, which is what they're really trying to do. They're trying to find the Active Directory, right? And so they'll ask, where is it? Where is it? Who knows about it? that causes changes in the normal network communications that we would observe. In this case, these two computers may actually talk to each other normally, right? But they may not be talking on the ports that they are now talking on, or they may not be talking with the same number of bytes and packets, or even deeper into the packet contents itself. In the ways in which they're talking, again, we can quantify the deviation from what we expect between those two computers. Here's another one is, those two computers have never talked to each other before. That's pretty weird. How do you quantify how weird that is? Well, it's kind of tricky because, again, I don't want to say 0 and 1. I don't do that. So how do I score the probability that these two computers are going to talk to each other? And I've got some papers on that, and others do. We call it a new edge in the sort of network research literature. Obviously, there are some computers that have a high propensity to talk to other computers in a new way, new communications. That happens. There are servers that receive new communications all the time. That happens. So you can combine the sort of propensity for the source to make new connections and the propensity for the destination to receive them to get a probability for this new edge, for example. Okay, so I just described sort of existing edges and understanding what's normal with them, and then scoring this one. And also new edges where you haven't ever seen them talk to each other, and trying to score the probability of an observed new edge. I'm seeing, is this making sense to folks? Heads nodding? Okay, thanks. Right, so reconnaissance. Lateral movement, everybody's favorite. This one's really hard. It's really hard to find lateral. It's behavioral. They're usually using system tools. They may just RDP, right? Is RDP weird? Not really if you look at the whole network. It happens a lot. Admins do it all the time. SSH for you Linux nerds, which I'm one of them, ironically. So lateral movement's really hard. That's one thing to take away from this. But we can score combinations or paths. Gabe was talking about paths. We can score unusual paths in the network. And I've got some papers. Others have some papers on that subject. We can score the processes that are running to allow for remote communications like WMI or WinRM or SSH or RDP. There are processes here, right, that are associated. So the endpoint has stuff running on it, and the pair of communicating computers has some signal in it, and we can score paths in order to find or quantify our belief that this is not lateral. That was weird. That was a weird statement. Again, I flip it around. I'm always looking for normal, and I'm looking for evidence against normal. And that's what these scores are. In statistics, we'll call them p-values, by the way. OK, here's another little bit of cartoon is, all right, they found all the data that they wanted. Maybe it's all the credentials from your Active Directory. That's bad. You don't want that. And they may need to consolidate them into a single place just for convenience or actually to try to stay quiet. So this is known as data staging. They'll move stuff from a variety of sources in the network into a central place, and then they'll tar it or rar it or zip it or whatever, and then they'll steal it out of the network, exfiltration. And again, volumes of data flowing to a central machine that are unusual with respect to models that we expect are going to be able to flag this. So if you have bytes and packets, you can see the aggregation of data into a central machine that is unexpected from what's normally happening on that machine. Sort of vertex-based, and this is like an in star. The reconnaissance is like an out star from a vertex. These things are like paths. Exfiltration, lots of stuff you can do here. The reputation of the machine that you're talking to, how unusual the communication between the two machines are, what was happening process-wise on the machine, the amount of bytes modeled as a time series over time between this computer and this other computer or maybe any computer on the internet. Lots of stuff you can put together, none of which is a smoking gun. I'll tell you another story. So another way to look at this is flip it on its head. This is how we can sort of track it and quantify it. But what if you miss it? So let's say, I'm going to pick on Microsoft a little bit, which is ironic. I work for Microsoft. I'm a very happy Microsoft employee. But I'm going to pick on Microsoft because it's the enterprise software that we deploy and sell all over the world. So, and I say this because my brothers and sisters in Office are working just as hard as I am to defend these enterprises, okay? So we have Office. It's got Office 365 has great phishing detection, some wonderful people that do incredible things with deep learning and really, really impressive machine learning work over there. And yet, they'll see something come in, and they know they've got a little bit of signal for it. They say, I don't know, 0.01% chance that it's a bad guy, right? Or a phishing email. They get emails, right? Exchange servers and things. And yet they know, the researchers know, they'll be looking at that data, they know it's a phishing email. And they can't fire on it because if they do, they'll have 40,000 false positives. Half our customers will be mad at us. False positives, right? Customer pain. Analyst pain, they hate us when we do that. So even though the researchers know that's a phishing email, we know it, they have to let it go through because at scale we can't fire on that without a bunch of false positives, okay? So it goes through. Goes through. Then zero-day exploit, right? It gets on the endpoint. Windows Defender, researchers know, we can see it. We can't fire on it, 50 million false positives. And those guys have massive scale. So AV, you fire false positive in AV, man, you're dead. Like, everybody hates you. Like, you're hated. So we don't fire. And then all of this other nasty stuff happens, and the EDR can't fire because none of these things are strong enough in isolation to fire on them without too many false positives. And this is how breaches happen, and this is how nation states penetrate our networks and steal our data, is because any one of these individual things isn't strong enough. And so that's why graphs are important, is because we can use graphs to consolidate all of this together. All of these weak signals that in isolation we can't fire on because too many false positives, together can be extremely concerning. Holy crap, we saw this. Yeah, it's pretty unusual email, but also all the evidence from the endpoint and then the lateral movement in the network. If you put that together, it's instead of like 0.01 chance it's a bad guy, it's like 99% chance it's a bad guy. So there's like a multiplicative or geometric effect on the probabilities being correlated together in the right way, and that's where the graph comes in. That's why the graph is important for us. It's the way to connect all of the attack data together and make it stand out of the noise. So that's the next thing I'm going to talk about. Here's another cartoon. This is just like putting all of that other stuff I just talked about together into one graph, and then I'm putting little Greek numbers on all of the nodes and edges to represent the scores that we have extracted from each of these behaviors. Okay, and so now imagine again that this is the attack. We know it. Well, here it is. We found it. But actually finding it is really hard. That's what we try to do. So imagine that this is. Do I have another slide? Yeah. So this is embedded in that. Right? So like this tiny little thing, it's tiny. And again, this is a ridiculous graph, completely unusable. The reason I'm putting it up there is to show you it's impossible to find this and that. Or is it? No, it's not. It's not impossible. We can find it. And we can find it through finding a subgraph of scores which are connected and consistent with the attack behavior within this giant graph. So that's what I'm going to sort of talk about next is, given Actually, next I think I'm going to talk about how to get some scores, and then I'm going to go into a little bit of statistics, and I'll watch people fall asleep and so forth. And then I'm going to talk about how to, if you have a graph with scores on it, like every node and edge has scores on it, this whole thing, how can you find this little tiny bit within that? Okay, so that's sort of a sketch for the rest of the graph and rest of the talk, and I should look at what time I've got. I'm okay. I'm okay. Right. Here's how to score an edge. One way to score an edge. This is number of failed RDP logins from the internet to a given machine inside an enterprise. Okay? And man, it's a mess. So, and I apologize, like it's probably hard to see. But the red line is a statistical model. What is it? It's a zero inflated negative binomial with seasonality. Fancy, fancy. It understands the time of day. It understands variability between what we expect and what we're observing. So the blue dots are the number of logins, number of logins. The red line, you can sort of see it here. Sorry about I should make that line thicker. These humps are days, right? You can see that from the data. You can see here's a weekend. So this machine doesn't receive a lot of incoming failed RDP login requests on the weekend, or less than it does during the week. The distance between the line, which is the model, and the observed blue dots, those are the number of logins we've observed, okay, is a way to understand the deviation between what we're observing and what we expect. Make sense? Everybody okay? We're going to dive into the deep end here. It's actually probabilistic in that it's not like a Euclidean distance. It's not x minus mu quantity squared. It's the probability under a parametric model, negative binomial, of observing this data given that we've learned over time what's normal. This guy was observed. There's a blue dot there. 80 logins per minute happened for 1 minute on a Saturday in March. That's a successful brute force login. So we found it. And we found it by quantifying what's normal and then calculating these deviation scores, these alpha i's. So that's a way to score. So let's go back and say, like initial penetration, I talked about a phishing email. In this case, it's a brute force RDP attempts where they're guessing a password. And yep, they guessed the right one. And there was a successful login after this. And a breach happened, OK? OK. So that's how you score. That's one way to score edges, communications between the internet and a machine, OK? But you can also score nodes. Man, that's cool. What is that? I'm just kidding. I know what it is. This is a PowerShell. This is a representation of a PowerShell script that ran on a given endpoint. Okay, it doesn't really look like a PowerShell script. It's an embedding of the PowerShell script as elements in an embedding. So they extract the text of the PowerShell script and convert it into some numbers. And then I'm sort of skipping over some details because actually there's a deep learning model here, and but it gives you some numerical understanding of the semantic relationship between the words. By the way, Amir Rubin, a colleague of mine in Israel. And so, like, you can see that, like, logical statements are close to each other, right? Which actually is a bit of magic because we had to convert natural language into a quantity in order to put it close together, okay? And so, and you can see downloading and sort of web behavior is close to each other. and things like that. And so this kind of semantic understanding with a computer, if we were in the Living Computer Museum, so that makes sense, we should do that, is how we've encoded a PowerShell, which is sort of a human language. It's not really, it's a machine language, but sort of the human level of it, into something that we can then score and quantify, again, the deviation from what we expect and what we're observing. In this case, it's on a node. It's a script running on a computer. Okay, and we can say, yeah, that one has a score associated with it, and we can quantify that. In this case, this is actually able to find attackers on its own as well, because attackers write PowerShell scripts that this thing will pick up. And there's a supervised machine learning approach, for those who are wondering, supervised machine learning approach that makes a decision, is this a malicious PowerShell script or not? But what I want to, again, get across to you guys is, in addition to it making a decision about this PowerShell script, it can also extract a score, which in this case is the distance, some probabilistic distance between the decision line of the supervised classifier and the observed point. Okay? So instead of thinking it's bad or good, I think it's 0.79. And I'm going to take that score, and again, I'm going to combine it. So this is an example of a node score. We had an example of an edge score. Now you guys know all about scoring nodes and edges. Next. OK. So now I'm shifting gears a little bit. Now assume we've scored all the nodes and edges. Everything's great. Scored all the nodes and edges, but we still have to find that subgraph within that giant graph, right? How do we do that? And so this is a real attack, again. And I'm going to describe one algorithm. I'm going to walk you through a couple algorithms for finding local subgraphs of attack behavior given a giant graph with scores on the nodes and edges. And so first I want to say, like, the nodes, again, in this case, are computers. The lines between the nodes are authentication events in this case. Credential usage, either Kerberos or NTLM. And the color is proportional to the score I've put on the edges. Remember, I was scoring the edges. I've just made a pretty picture that has the score, the color proportional to the score that I, under the hood, made. Okay? And so here's a greedy algorithm for discovering within this larger graph the subgraph that I want to show the analyst or I want to alert on or whatever. And the way I'm going to do it in this case is heuristic. It's a greedy algorithm. It's going to say, find the score that's smallest. Remember, I've got scores on all the nodes and edges. So find the smallest score. And I, when I was making these slides, I just had like an algorithm. Like, I could write a while loop here. So that's what I'm actually just talking to you about, which is, find the alpha, which is smallest, sort all the alphas for the nodes and edges, all the scores. Find the smallest one, start there, crawl along the graph. Find the weirdest next hop, collect that score, combine it with your score. I might have a slide about how to combine scores together. There's lots of papers about doing this. And then have some stopping criterion, like we can no longer collect more badness, stop and report. Simple, greedy algorithm. Try to find the subgraph of most anomalous or most concerning scores, okay? That's one way to do it. So here it is, a build of that. Oops, that node looked weirdest after the edge. Oops, that edge looks weirdest. And then just recurse until you're done. Some kind of stopping condition, okay? Oh, by the way, you can see there, that's reconnaissance. Remember I was talking about they like reach out and try to find the next place to go to. That's what they were doing, and then they moved down here, and then they moved over here. Okay. Here's another one. It's really hard to make slides that explain this well, so I'm just going to have to talk you through it. Apologies. But instead of having like a greedy algorithm, because you might because of signal and noise and data collection and all kinds of other things, you might miss an edge or a node in that greedy algorithm. Or maybe that the attacker just didn't introduce very much signal and move in through that edge or over that node. But then they become more evident later. And so you could think of some randomization to allow you to hop over normal edges or normal nodes to get to more weirdness, and you could try to do that algorithmically. That's a good idea. You should try that. That works. But also another way to do it is to sort of define some templates and then search for, and then enumerate that template in your giant graph everywhere you can. Collect the scores from those little small templates, like here's a path and here's a star. Those are templates that I'm going to slide over the whole graph. I'm going to enumerate all the paths of length 3. There are 3 edges in this one. I'm going to enumerate all of them. 4 billion, 400 billion, a trillion. There may be a lot of them. And I'm going to calculate some combined score across all the alphas for that path, for all those paths. I'm going to do it for all the stars. And then I'm going to threshold. I'm going to say the combined score for these objects. I'm going to find the weirdest ones, and I'm going to report those to the analysts. So subtle difference from the greedy one is here. I'm going to define a template. I'm going to slide it all over the whole network. And I'm going to try to find the weirdest subgraphs because the scores are all saying, yeah, that's weird. OK. And there's a paper if you want to read it. There are problems with this, I tell you. When you start enumerating paths, and Gabe knows, I'm sure Gabe knows, you get a lot of them. There's a lot of false positives. This suffers from what statisticians would call a multiple testing problem. So issues with this, to be sure. But it's another method. OK, and now spectral methods. These are among the more cutting edge in our research team. So let's see. And I don't have this up on the slide deck, but an adjacency matrix. Some of you will nod your heads. It's a matrix. I don't mean Keanu Reeves. In the rows are nodes, and in the column are nodes. And I'm going to put a 1 if there's an edge between a node on row X and a node on column Y. And that's an adjacency matrix. And I don't have that here, but it's just a giant matrix that describes the connectivity of the nodes and edges. Okay? And you can do all kinds of linear algebra with that. And you can take that holistic graph and you can look for spectral embeddings. Basically look for, decompose it into eigenvectors and eigenvalues, and then find the right eigenvectors and eigenvalues that represent the kind of shapes you want to pick up in the graph. And remember, the kind of shapes we have, they look like that or like that, right? And so we can design spectral methods that identify the combination of nodes and edges with scores that are unusual from a spectral perspective. And boy, I'm waving my hands a lot. This is not simple stuff. There are papers here, and this is hard work, and I think it. So 2 methods to sort of describe. One is, imagine you've got a time series of graphs. So you observe this thing, let's say, over multiple time steps, which is actually what's happening here. The nodes and edges are time series models. And so we're observing this over time. But in the setting of spectral methods, we can observe whole graphs at a time. Like in minute 1, we have this graph. In minute 2, we have this graph. They change subtly. And this particular method is about identifying those changes from a spectral approach in the sequence of time series of graphs. And that's about all I should do. I'm going to murder you guys. That's probably already too much. Another way to do it is to, again, use a spectral embedding from the adjacency matrix, or something they call the graph Laplacian, and then identify clusters in the in the embedded graphs in terms of those nodes and the scores on the nodes and edges. And so I don't think you're going to be able to extract a whole lot from the words I just said. It's actually quite hard to explain here, and there's a paper in the works that we'll publish. But by the way, we can find attackers with it. There they are. And I skipped ahead, but here they are. These are them. Actually, these are us. That's me and my team doing weird logins between each other and able to find that as the most anomalous thing. So, research. You know, we're trying new stuff out here, and I think it's going to work. And I'm very excited about the next set of spectral methods here. And I think that's about it. Well, you know, there's a lot of people that work on these things, and I tried to give credit where I can, but man and my team are rock stars, and I'm so proud of working with them. And so they did all of this, and so I'm really, and that's it. Questions? Let's start. You were the first one to go.
Thank you. The time difference between the start node and your end node, what time width are you using? Or have you found an average one that works well, or do you modify it based on what you're looking for? And how much does that translate into, obviously, the massive number of nodes you're keeping in memory and the data storage requirements?
Yeah. So let's see, there was a whole bunch of questions there, but they're mostly about time. And I think they're mostly about the time period that the attack takes. That's a hard one. We don't know. Again, they don't tell us, right? And so as a former member of the US government, I saw Gabe as well. I can tell you in our observations in that space were anywhere from 5 minutes. This is interactive attackers, like not malware. Anywhere from 5 minutes to a couple years. So there's so much variability, right? And how do you handle the low and slow, right, versus the fast ones in memory, in compute, and all of these things? I don't have good answers. What I do have are statistical approaches. So there's these things called Q-sums, which are able to accumulate either point-in-time concern, like that brute force you saw where it was just like, boom, that minute it was completely crazy. But they're also able to accumulate moderate anomalousness or concern over longer periods of time. And it's a statistical decision as to whether you want to alert or not. So I don't have, I mean, I can tell you, anywhere from 5 minutes to 2 years, and that's not very helpful. I can tell you, we try to moderate our risk in not detecting those kind of things using control chart theory or statistical control theory to try to either capture those point-in-time anomalies or the slowly accumulating ones over time.
It's helpful that you also don't know. So.
Yeah, that's right. Yeah, it is. Thank you for your question. Yes, sir.
Hi. So at JP Morgan, we operate large data centers around the world. I'm curious, what of what you just showed is available out there in terms of open source code or research papers that would replicate your work?
So the question was data centers, JP Morgan. How much open source code is there and papers such that you can replicate this work? Thank you for asking, and I'm a scientist. I like to claim, well, they put in my title anyway. I'm not sure, but I do like to participate in the open source community. So from our work in particular, I would point you at my Google Scholar page to start with. I've got plenty of papers there. We are early days in my team of publications. We're working on it. So we're going to get you more papers soon. Some of this work was done outside of Microsoft, I should say, and you can see most of that from my Google Scholar page. I'm going to use this as a little bit of a platform. As the community wants our data and our code, and I want to give it to them. in a way that is compliant and preserves the privacy of our customers. So we have efforts in place to do anonymized data releases, which do compliant, privacy-preserving release, so that we can collaborate with our industry and academic partners. And that's not easy and requires a lot of work in compliance and in legal things in order to get past those hurdles. But I'd like you to know that I'm extremely interested in the collaboration that we can do with academics in an open source and an open way, so that you can bang away at our methods and try to find where they're not working, so that I can provide better security for my customers. So I absolutely agree with that sentiment.
And a follow-up question.
Yeah.
So this, I can see how it operates great, perhaps at the infrastructure level. If you're a customer of Azure, a customer of AWS, and you deploy SIEM tools, how much of the data that this model requires can be sourced by a cloud customer, not a cloud infrastructure?
Yeah, and so let's see. Let me try to repeat that question. So a lot of this is from infrastructure. So I think by that you mean on-prem, like sort of an enterprise's.
No, say we have a large presence inside Azure.
Yeah.
And would like to apply the same type of tracing where things originate and come from, but do this
in Azure
at the level of the applications we deploy.
At the application level.
Services we deploy.
Yeah. Yep.
I'm really sorry, but
Yeah.
we're gonna have to break for lunch.
Okay.
So if you have like other like questions or comments, Josh is gonna be here parked for the stage however long you want. But for the rest of the folks, lunch is actually being served, and I want our like workshop to get a head start and not stand in line. So you can just go break for lunch. Josh is gonna be here, so please don't feel obliged to stay. Okay, thank you.
Thank you.
Yeah. Okay, Mark.